Alright, so in this video we will be covering the probability of single and multiple events. And so you're going to see the pages in the book of probability where all our notes have been going, and make sure you're on the right page to get started. So first we have single events, and this section is titled the addition rule. And we kind of already talked about what I'm going to go over with our marbles problem from the last section of notes, but hopefully you recall that when we get to it. So, mutually exclusive is an important definition to know, and mutually exclusive is events that do not happen at the same time. So if you think about our Venn diagram, when events are mutually exclusive, they don't have any overlap in the center. And so they're just two separate sets. So there's one of them doesn't happen in concurrence with the other. So for instance, being a freshman and a sophomore. So there is no person that's going to be both a freshman and a sophomore at the same time. So this is mutually exclusive. Now if you can be in two sets at the same time, then it would be not mutually exclusive. So for instance, a musician and an athlete. You can be both a musician and an athlete. So that is not mutually exclusive. If I could get my circle to come up. There we go. Then we have a face card and a heart. You can be both a face card and a heart. A heart is a suit, and then all the face cards exist in that suit. So that is not mutually exclusive. And then finally, a spade and a diamond. Now these are both suits. You cannot be both a spade and a diamond, or you can't have both a spade and a diamond. So that is mutually exclusive. So for mutually exclusive, if two events A and B are mutually exclusive, then the probability that A or B will occur, so remember this is the union, if they're mutually exclusive, we can just add their probabilities together. So we did do an example in the marbles where when we said red or blue, now you can't be both a red marble and a blue marble at the same time, so we could just add these probabilities together. So for our example, we have a math class. It contains 7 freshmen, 11 sophomores, 5 juniors, and 2 seniors. And so if we're randomly picking a student to put a problem on the board, what's the probability of being a junior or a senior? So it's the union of these. Well, these are mutually exclusive. You cannot be both a junior and a senior, so we're allowed to use the addition rule right above. So the probability of being a junior plus probability of being a senior, there are 5 juniors out of 25 students, and there's 2 seniors out of 25 students, so together is 7 out of 25. Okay, then we have addition rule number 2, which is when events are not mutually exclusive. So if you recall the problem about marbles, when it's a not red or a not blue, now those do have some overlap because white and green marbles are not red and also not blue. So we have to account for that overlap when we're looking at this probability. So when you're doing a probability of mutually exclusive events, you add up the probabilities similar to the previous rule, but you subtract their intersection. Remember, their intersection is the overlap, and the reason for this is the overlap is going to be included in the probability of A, and it's also going to be included in the probability of B because the overlap exists in both sets. So in order to find the probability of the union, we have to subtract the overlap once, because it's counted twice, basically. So the intersection overlap that is counted twice is what we are subtracting out. And that's a important note to make. Okay, and then some examples. So a card is drawn from a regular deck of cards. We want to know the probability of being a face card or a heart. So face cards and hearts do have overlap. So the way we find this is the probability of the face card plus the probability of the heart minus the probability of being a face card and a heart. Probability of a face card, there are 12 of them out of 52. there are 13 hearts out of 52, and then there are 3 face cards that are also hearts. So we subtract the 3 over 52, we get 22 over 52, and then we can reduce this. So I would like you to try the next one without seeing my answer, and then I'll show you it, and then the third one you're just going to do on your own, and I'm not going to verify the answer with you, and we'll use that one in a quiz. So pause the video and try part B. Alright, so hopefully you were able to get part B, or kind of follow the pattern from the last one. You would be adding up the probability of being an even card plus the probability of being a club, and subtract the probability of being even and a club. So even cards. There are 20 out of 52. That's numbers 2, 4, 6, 8, and 10. So there's 5 of them. And then there are 4 suits. So that's where we get the 20 out of 52. Just like the last suit we were talking about, even though it's clubs and not hearts, still the same amount of them, so 13 out of 52. And then the even numbers that are clubs, there's 5 of them, so we subtract the 5 and get 28 over 52, which reduces to 7 out of 13. Alright, so that last one I'm going to leave for you. It's going to be incorporated in our quiz. Alright, so next page. We're going to use these examples, but kind of involve our Venn diagram that we've been talking about. So when I do my Venn diagram, I have 3 sets here. So what I've done is I've intersected the 3 sets. So right here is my intersection of x and y. Right here is my intersection of z and y. And right here is my intersection of x and z. And then in the center, where they all overlap, would be if there were any that intersected in all of them. So not all of these intersections are actually filled in. The only one is between x and y. They had the number 2 in common. And then the rest of them are just unique to the set. So I do have something in the overlap of x and y. So going through their probabilities, you can just look in the bubbles to see, how many there are. The probability of x, there's 2 of them out of a total 6, which reduces to 1/3. The probability of y, that would be this bubble right here. There is 3 of them out of 6, which reduces to 1/2. And then z, there's also 2 out of 6, 1/3. So the question is, are set y and set z mutually exclusive? So if they have overlap between y and z, they are not mutually exclusive. If there's no overlap, then they are. And we can see right here where those intersect, we don't have anything in those spaces. So yes, they are mutually exclusive. Therefore, when I do their probabilities, I can just add them together. I can add my 3 out of 6 with my 2 out of 6 and get 5 out of 6. Okay, for set x and y, we do have an element in the overlap here. So they are not mutually exclusive. And now when I do the probability of x or y, remember I have to subtract out that overlap. If you also notice, when we unite these all together right now, I can see that that 2 is in the overlap, and I don't really have to follow the addition rule, because when it's in a Venn diagram you can just see it. So if I was doing the addition rule, I would say 2 plus 3, but when I look at them all together I see that there's only 4, because this is only accounted for once in the diagram, even though it exists in both sets. So really, using the Venn diagram, kind of don't even have to worry about that rule. You do want to know both though. So I showed the rule here, but we could clearly see this is just 4 out of 6. Okay, so then we have using a frequency table. This is going to be a common thing, especially going to see this on the end of course. And right now all we're looking at, all we need to know about the tables really is, there's rows. So this is people who have gone to Europe. At the bottom is the total number of people who have gone to Europe. This row is those who have not gone to Europe. The bottom is total number of people that have not gone to Europe. So this, we can show like more intersections through sets with a frequency table, where in a Venn diagram, like all those sets together got kind of complicated, and this would be 4 of them. So then we have Canada. Total people who went to Canada is 25, and not been to Canada, total people who have not been to Canada is 9. So then we have these intersections. So this is the people who went to Canada and Europe, haven't been to Europe but have been to Canada, not been to Canada but have been to Europe, and haven't been to either. So then we have our probability. So when I'm doing the probability of Canada, I want the total number of people who have been to Canada, so I have to go to my total column. So that would be 25 out of the total 34. Also, the total sample space is always going to be in the bottom corner here. So then total that have not, probability of not going to Europe, there are 29 people that did not go to Europe. I have to make sure to get the total there. So 29 out of 34. Then the probability of not going to Canada, 9 people didn't go to Canada out of 34. And then finally, not Europe, Europe, not Europe, but Europe, 5 people have gone to Europe out of 34. So some of our probabilities we were looking at previously were about, rolling dice or some event, but sometimes we come up with these probabilities based on things that have happened, and that would call it experimental probability. So to continue on with probabilities, now these Canada, or not Canada, Europe, or not Canada, I need to figure out first if these are mutually exclusive. So can you exist in both of them? Well, E is a good example of being mutually exclusive. Canada, going to Canada and not going to Canada, there's really only 2 options. So you've either gone or you haven't, and that's a good indicator of something being mutually exclusive is they'll be in rows together. So like there's not an opportunity for these 2 rows to intersect. So we can just add the probabilities together here. So going to Canada is 25 out of 34. Not going to Canada is 9 out of 34, and together we get 34 out of 34, which is 1. 100% of the people surveyed either went to Canada or did not. Okay, so now we have Europe or not Canada. Now these are going to have an intersection. If I look at Europe, it's right here, and then not Canada is right here. So where they intersect is 2. So that's their intersection that I'm going to have to subtract. So the probability of going to Europe, the total was 5 out of 34. The probability of not going to Canada was 9 out of 34, and then we had an intersection of 2, which I need to subtract because it's being counted in both of the individual probabilities. So when we do that, we get 12 out of 34, which reduces to 6 out of 17. And then we have part G, Canada or not Europe. So Canada or not Europe, the total for Canada, ooh, I messed that one up. The total for Canada should be 25 out of 34, not 5. And then not Europe is 29 out of 34. So make sure you adjust that. I made a mistake there, and I think you guys can pick out my mistake. I just told you. How about you fix that and come up with the right answer? Okay, so moving on. We have multiple events, the multiplication rule. So, if you're rolling a die and flipping a coin, the sample space of the first event is 1, 2, 3, 4, 5, 6. Those are all the options for rolling a die. If you're flipping a coin, the sample space for that is either heads or tails. There's 2 outcomes. And so, yes, we don't always just have numbers as our data or our elements in our probability. Sometimes it's going to be heads, tails, green, blue, whatever it is. We might be listing out letters or names. So, is the sample space of the second event affected by the sample space of the first event? And that is a no. So, whatever I get on my die is not going to change or affect what I get on my coin. So this is an example of independent events. The outcome of the second event is not affected by the outcome of the first. They're independent of each other. They